So, hello everybody. Thank you for coming to this stage. This is a Java developer stage. Are you Java developers by any chance? Hands up. Good, nice. So we are in the right place. My name is Anton. I work with a company called JetBrains. We are famous for building tools for developers, not only Java developers, but the others as well. And hence my presentation today is about the tool that many developers love, the IntelliJ. And more specifically, I will be talking about the debugger. And I hope that the showcase I will be doing today will be useful for you tomorrow or whenever you come back to the office. So at least one little thing, if you learn from this presentation, that will not be a time wasted. So I have only the code. You will find it in GitHub on my account later. And there are a few demos. We will go through those demos one by one and look at the specific features in the debugger. How often do you have to debug? Once a week. Once a week. Yes? Many of you. So you probably know the basics. I don't have to teach you the basics, but I will try to go a little bit beyond that and show you the little things that are somewhat hidden in the debugger under the UI elements. Let's start with a feature that does not really belong to the debugger. It's rather a runtime feature. And it's called hot swap. It's been there since Java 1.4. And different runtimes, meaning the different JVMs, have actually different capabilities for this feature. And the debugger in this case features as an interface for this feature. So let's look at that. We can run the application in the debug mode, then this feature becomes available from the runtime to us, and we can interact with the running JVM. Either running locally or remotely, it actually doesn't matter. And we can inspect and change its behavior, either by adding new code to it or triggering some commands to change the behavior that will be different from what we anticipated when we wrote the code. So let me demonstrate that. I will be running this program. Actually, let me explain first what it does. It's a simple loop. It prints out something. It gets a value from the other class that builds a string out of the numbers. So it concatenates a string out of the numbers. And it also reads something from the input. So whenever I input something in the standard input in the console, it will also concatenate the value that I added. So let me run this application in debug mode, but I will not run it from the IDE. Instead, I will run it from the command line. So why I would like to do that? Because pretty often people ask me how to connect to a remote running process. So imagine that currently the terminal is a remote machine. It's my machine, but it's a remote process in regards to the IDE. To run a remote debugger, actually the IDE helps you somewhat with that. There is a type of a run configuration called remote, and it provides you an option to enable remote debugging in your process that you want to debug. So you need to add this JVM option that enables this wire protocol and specifies the port where you need to connect. So this is the default configuration. And if I copy this line from the configuration right here and paste it into the command line right here, so that's the command line I'm running with, it will run this program, but in a terminal, not from the IDE. Let's do that. So it opens a port for my debugger to connect, and now it does something, right? Apparently it should be waiting for something. So the application is running, and let's connect to the application from our debugger in the IDE. I'm running this remote configuration instead of the local one. And the debugger is connected, and nothing is happening. The program is running. We don't see any indication of activity right here. Or sorry, Where is the command line? Right here. So the debugger is connected to this process. Let's actually move it to the right so we could observe the output as well. Right top, right here. So because we need to see the output as how it changes of the program. Now let's inspect what is going on. The program is running and we don't know where it is, what it is doing. And at this point we can actually pause the program and inspect the stack trace, what is going on there. So apparently it's stuck on the reading the bytes, waiting for the input from this line, and where it was triggered right here. So if we input something in the standard, in the IDE, right, in the terminal actually, 1, 2, 3, 4, 5, 6, it's going to be doing something, right? So what we want to do is to jump out of this loop somehow and maybe set a breakpoint right here. In fact, well, everybody knows how to set a breakpoint. You click on the right. There, of course, is a shortcut, but you probably didn't know about this trick that you can add a cursor, or sorry, multiply the cursor and set the breakpoint right at all the lines. That's just a neat little trick, not so useful. And let's let the program run so we see the output, some output from the program now, like it was printing out. So it printed it right here. And we can see the inlay values of the various variables. And while we are at the breakpoint, we can actually not only inspect and see the internals of the program, internals of the frames, we can do a few modifications like that are not like something, not a rocket science. There is no trickery. It's all enabled by the runtime and the debugger, and the IDE is just an interface for that. So, for instance, we want to restart this function that we are in. We can drop the frame and just jump out of this method and restart it again. Right? It's like we are going back in time. Although it changes the behavior, but it doesn't change the state. So if you change the values of the fields and you change the state of the memory, it's not going to be rolled back. So you have to account for this. Let's jump into this method again. Well, it's waiting for something, but like it's waiting for the input again. Let's change it so that it's not waiting. It will not be waiting for it that much. It will not be requiring us to input too many lines. So what I did now, I changed a single statement, like the for loop. I recompiled the class. The debugger noticed that there is a change in the file system of the timestamp of the class file, the file itself. And it offered that, hey, do you want to reload this new bytes in your runtime? And I submit it, and now it tells me, okay, 2 classes have been reloaded because actually in this file I have 2 classes, right? But what happened is that I replaced the frame with new bytes. I replaced the method definition, but the program is waiting somewhere in the native frame. So on the next run, the change will not be applied yet. We have to jump out of the frame so that the stack is cleared and the JVM can put a new frame on top of the stacks, then the new behavior will apply. So let's trigger that somehow. Yeah. So you see, like, it's the old behavior. We have 5 numbers concatenated in there. And if we let the program run, so we hit the breakpoint, sorry. Where are we now? Okay, we are still waiting for the input for some reason. 1, 2, 3, 4, 5, 6, 7. Still waiting. So I managed to get the program into a very strange state. But let me restart, because I want to show a few other features. Still with the remote debugger. And I will remove the reading part. So I just stop at the breakpoint without reading from the input. Okay. So we hit the breakpoint. And what else I can do is I can reset the variables. For instance, right here, it still waits for the input. I can, for instance, change the value of this loop variable into something like 0 and start from scratch. Or I can change the builder value somehow and also change the output of the method and the result. And what I wanted to show, let me show it locally now, not from the remote debugger, is forcing some behavior on the application from the debugger. We can see it's now running the new code. Let me reload it slightly so that it changes the behavior, and we can see the effect immediately. But if you stop at the breakpoint right here, and imagine I want to experiment, I want to force some other value to be returned from this function. There is a force return functionality, and I can say, okay, I don't want whatever this function was producing. I can say that I want a specific value like hello to be returned from this function, and it will print hello to the output. Or I can experiment even more and say that it's not just the return value that is interesting for me, but I also want to verify how the program behaves if an unexpected situation happens and throw an exception right from here, like this, for instance. So of course, in this situation, the application crashes, but it's a tool for you to experiment, to see how the application behaves and how it survives whatever is happening, whatever your changes are introducing. So it will show me that it crashes. So that's the first feature. It's actually a runtime feature. It's enabled by Java serviceability, and this is the strong foundation for all the tools to build on. The debuggers, the profilers, monitoring tools, everything is using these APIs and this protocol. Let me go to the other features that we have in the debugger that are probably more interesting. So in 2014, we got lambdas in the language. Do you remember that? Java 8, we got lambdas. Everybody started using them in conjunction with stream APIs and started to write long expressions in one line because it's fancy, because it's nice, because it's so beautiful. And the debuggers were not ready for that, because the only way to debug such expression was to set a breakpoint on a line. But you have so many expressions in one line. Now you have to break the line somehow to put the breakpoint on a specific expression that you want to debug. This is not something very convenient because you have to change the code, right? So that was just the lack of tooling. And since then, IntelliJ introduced lambda breakpoints. So that's not just a single line breakpoint, but also every individual lambda expression could have its own breakpoint. So if I set that, can you see that it's mildly colored red, right? So if we set the breakpoint right into this first expression, and run or debug the application, you'll see that it hits that specific lambda expression, not the whole line. And well, okay, we hit the first breakpoint, but we have multiple expressions on the same line. How do I go to the next expression? There is a functionality called run to cursor. So if we, if we set a cursor into the next expression and hit the action to run to the next cursor, it stops right there. Okay, that's a nice feature. We can use that. But, well, if we have a lot of data, we cannot trace every lambda expression for every piece of data. It feels unproductive, so it seems that the tool is giving us something. It's convenient to use, but it's not that convenient in regards to our goal right now, to understand how the logic and how the data flows through this transformation pipeline. So what we could do instead of lambda expressions, let me stop the process. We set just a normal line breakpoint right here, right? The line breakpoint, and run the process again. It stops at the line. And how do we get into a specific lambda that is interesting to us? In IntelliJ Debugger, actually in any debugger, there is an action called step into, where you want to step into a specific invocation and proceed from there. When you have multiple expressions or multiple invocations on the same line, there used to be an action called smart step into that offers you which expression you want to actually step into. And now the behavior is slightly different. You can actually use the normal step into action, and it will immediately analyze the expression that you have on the same line and offer you what do you want to do. So if you do step into, you can see it's highlighted and it offers me, okay, you probably want to go here because it remembers from the history which one I selected, but I can just select whenever I want, whatever I want. For instance, this expression right here, hit enter and stop right there. So it's slightly more flexible in regards to the first workflow that I demonstrated, but still not as powerful to debug such streams. So what we could do instead, when we stop at this breakpoint, there is an action called trace current stream chain. What it does, it analyzes and actually emulates the process that is described on this line. And it runs like evaluate expression, but it offers you a nice UI. So we could analyze the stages, like what was the input, what was on the next stage, how it transformed, what was the next stage. We see that it filtered one element, then it changed the value from string to a user. It's a custom object, and then we finally have a result, and we could actually flatten the mode. If it fits into your screen, then, well, it's nice. If it doesn't, then it's probably better to use this step-by-step mode. The primitive values are easy to observe, right? If you have strings, if you have numbers, then they're rendered pretty nicely. But if you have custom objects, then you either need to have either a good toString method, which is not always the case, or maybe this toString is too big or not convenient to use in this screen. Then you can actually create your own renderers in the IDE. For specific types, you can choose, okay, for this specific type in the debugger, I want to show only the specific values from the properties of that object. And we also can have renderers for like specific types, like collections, arrays, and so on. Okay, so let me check. Who learned something new today already? Nice. I hope you will learn something else soon. Breakpoints. So we know about breakpoints. We can set the breakpoints at any line of your code. But there are different kinds of breakpoints. We can set the breakpoints on the expressions or the statements in the code. We can set the breakpoints on methods, which historically wasn't a very popular thing to do because it slows down your application very much, and therefore in IntelliJ Debugger, method breakpoints are emulated. So instead of setting a breakpoint to a method, IntelliJ will search for all the methods where we want to set the breakpoint and put the breakpoint into a first line of the method. So it's kind of emulated. For you in the UI, it looks like a method breakpoint, but internally it behaves like a line breakpoint. So where is it useful when we talk about method breakpoints? See the code here. We have an interface with two methods, like foo and boo, and we create an instance of that interface and invoke some of the methods. So what we can do is to set a breakpoint not on a specific implementation, but rather on an interface method, which then behaves like a wildcard. So I will set the breakpoint to all the implementations of the base interface. So how it behaves, if I run the program right now, I will hit the implementation. You see the breakpoint was set automatically because I set it into the interface. And well, this way I was able to catch the implementation. However, in this specific example, it looks very naive. Why wouldn't I do it the old way? For instance, set a breakpoint on a line, hit it, and do a step into, and end up in the same place, right? So it doesn't seem too, like, nice feature, but doesn't seem too useful. So because Java is statically typed language, but has a dynamic runtime where we can use all kind of magic things like reflective invocations, bytecode generation, and so on, sometimes the static analysis tools cannot help you by saying that, well, this foo function seems to be unused. If I do find usages, it will tell me, hey, there is no implementation, there is no usage of that interface function. So what I could do to catch that, and why would I do that? Maybe my application actually manifests the behavior that I know was implied by this function here. So let me set a breakpoint. So I remove this one and run the program. Actually debug it. And I see that, oh, this foo function was actually invoked. It's running and it's doing something. So what happened? How could it be possible? Because this function was actually invoked through the reflection. And even though the static analysis tools could be smart enough to figure it out that there is a string that is used as a constant for a method name and find it for you, still this expression, this string or the method name could be a result of some expression. So you can dynamically concatenate the string, like in my case right here, and the tool will not be able to evaluate it anymore because it's appearing in runtime. So method breakpoint is a very useful feature for discovering runtime behavior that is not possible to discover through the static analysis. But what else we can do with breakpoints? What is really interesting is that we have parameters. But before I show that, I will show you a few tricks with the breakpoints. Imagine you set a breakpoint right here. You have configured it somehow, like there are checkboxes, you have configured the parameters, and suddenly you realize that, oh, but I wanted to set the breakpoint on some other place, in the previous line, for instance. And then, you know, all the configuration, all the work you have done is kind of void. And instead of unsetting it and setting it on configuring on the previous line, I could actually drag and drop it. So that's a neat trick. Okay, so what we could do with this line right here, if I set the breakpoint in this inner line, like where I see the instance being initialized, and I run the application, well, I hit the breakpoint only once, right? I will hit it here. If I let the program run, it will just print the line and say that, okay, we have always the same reference. And imagine I'm trying to debug the behavior of such a process, of the initialization process. So what I could do is to stop at this breakpoint right here and every time change the value. Every time I hit it, I set the instance to null, then this check is true, and then we create a new instance. Actually, using a non-suspending breakpoint, by letting the breakpoint not to suspend like this, I can automate this behavior by adding a statement into the evaluate and log. So whatever expression you can come up with, you can paste here. Actually, it can be a code snippet even, and log the result of that expression. So in our case, it's going to be instance equals null. Done. So the program will not suspend at that breakpoint, but it will just run that expression that I added and set the instance to null every time. So when I run the program, I will see that the reference is always different. Right? There are some other things that you can do with, like with the settings. For instance, if we want to pass this multiple times, let's say I want to enable this breakpoint or trigger this behavior only after it was hit 3 times, and then remove it. And then when I debug this application, I will see for the first 3 times, it was one reference of the object, and the expression triggered. We removed the breakpoint, and now we have a different instance all the time. That's it. That's a nice way to automate some of the debugging process in your application. In fact, what else we can do with those non-suspending breakpoints is to be able to debug complex workflows when you have a data flowing through different processing stages in your application. For instance, we have a workflow that calls the process method with some parameter. It goes from the process method into the step 1, from step 1 to step 2, step 3, step 4, and so on, and it converges in the output method. So we still have this idea right here. And to visualize this workflow somehow, actually in IntelliJ we have a static analysis feature that helps you with that. That is called data flow 2 here, because we are somewhere in a very deep part of our code. And if you run it, we can see that it shows me, okay, there's the output method, and it shows me the backtrace to the very first invocation where it was started. So we get back to the process method. Actually, in this case, I wanted to see how it branches out. So for me, it's better to see how it goes from, not from here, but not to here, but from here. Analyze data flow from here, and it shows me how from the process method, the ID is being used and how it branches out in step 3 and step 4. Okay, but what if step 4 is, the logic in step 4 is what is actually interesting for us? How do we stop in the right place that is interesting to us, like in the output method, for instance, but only in a specific branch of the execution? You see, the output method is being invoked from all the branches in my application right now, but I am only interested in the specific branch. What I can do is to set a non-suspending breakpoint right here. And by the way, you can do it quicker because it's evaluate and log, so you can actually select the value like this and click shift click right here, and it will be immediately the intention for the debugger that you want to set a non-suspending breakpoint and log the whatever you have selected. Done. Okay, so we have a non-suspending breakpoint at line 248. And in the breakpoint, in the real breakpoint that is interesting to us, we can now set a condition, not a conditional expression, but enable it only when a specific line or a specific breakpoint hits. So in this case, the non-suspending breakpoint is the condition for us to stop finally and analyze the application, right? So we leave it enabled. We are dependent on the non-suspending breakpoint right here. And you can see that it's disabled right now. So this like non-filled breakpoint icon means that there is a breakpoint, but it's a conditional one. It's disabled by default, and well, the tooltip tells you that it depends on a specific line. Okay, so let's run it. And we hit the breakpoint, and to prove that we actually were passing through the specific line, so the condition was met, we can see in the stack trace that, you know, here it is. We passed through the condition with the non-suspending breakpoint triggered, and then our breakpoint was enabled. Good. So we have a few more minutes, and I have a few more features to show you. Concurrency test. So concurrency is hard, right? Concurrent bugs are harder even. So I have a test that we can run, and we'll see that it passes most of the time, but it can fail. So what this code does, it just asserts if some size of a collection, of a list, is 1, and if it's not 1, it will fail, right? What the work function is actually doing, it creates a synchronized collection, synchronized list, starts another thread where it will try to add a value. And we will try to add a value from the main thread as well. So we are doing it in 2 threads, in the main thread and in the concurrent thread that we started. It's the same value, and the logic of that function is that it will check if there is a value of this, or the same value in the list already present, so it shouldn't be adding. If it's not there, it will add it. So if you run the test, run it, we'll see it passes. We can run it again, it will pass, right? We can do it many, many times, and we suddenly are unlucky and we will run it and it fails. So how to do that, how to experiment, and how to go about this kind of situation. In IntelliJ test runner, you can actually set it to run multiple times or until failure. So under the modify options, we have repeat option. Currently, by default, it's set to once, but you can set it to until failure. So let's try that. Maybe it will fail, maybe it will not fail. If you are lucky, we can observe it failing. Yesterday I was running it. It took me 100,000 iterations to actually fail. So let's wait a few seconds. We will try it again, because sometimes it takes a long time and sometimes it fails immediately. Okay, let's stop it. Let's try it again. If it doesn't fail, nothing bad. I will demonstrate how it fails in the debugger. 1, 2, 3, 4, 5, 6, 7. No, it doesn't fail. So let's go into debugger and see and prove that it can fail. Using the breakpoints, we can set a breakpoint to suspend not all the threads. That's the default behavior. We can choose to suspend a specific thread that hits the breakpoint. Currently, we have 2 threads, so 2 threads should hit the breakpoint concurrently. Let's debug the test. When we hit the breakpoint, for both threads, in this case, it happens almost immediately, almost at the same time. The debugger will tell me, OK, you have stopped in the main thread, but there is actually another breakpoint reached by the other thread, and you can switch to that. So I can verify, aha, I'm now in the other thread, and what I see is that my main thread has hit the breakpoint and thread 1 has hit the breakpoint. Interesting. Let's experiment. We are at the condition line. So in thread 1, let's step over. We have stepped over in thread 1. Now if we go into main thread, we can see that it's still in the previous line. What if we step over again? Because thread 1 did not add a value yet. We are both there. So both threads are currently on the line which is adding a value. Now we step over here. We have size 1 right here. We go into the different thread again and step over. And we have size 2 suddenly. And now we let it run. Sorry. And it fails. And it tells us that, hey, the expected was 1, the test failed because we have 2 values. So we kind of have proven now that the test can fail. How do we fix that? Well, we probably need to synchronize the list somehow. For instance, well, let's be naive and do it like this. And the ID tells me that I'm doing it wrong. Let me do that. So I should wrap with unmodifiable list. OK. And debug it again. So I'm setting a breakpoint. And debug the test. And now I can see that only one thread is hitting the breakpoint at a time. There is no other thread in the synchronization block, right? So we kind of fixed our bug. I will not try to prove it because, like you have seen, it sometimes doesn't hit, and I'm pretty sure we have fixed the bug right now. Anyways, we have a couple of minutes left. What else do I have in the list for you? So I was talking about renderers, and renderers are like a big topic, but still I want to touch a little bit upon it. We have different objects in our applications. Some of them are pretty large, deeply nested object graphs. And when we debug the application, for instance, we have a client, and client has like a company, a Twitter, and so on. So when we debug it and hit the breakpoint, here in the watches view, we have the values, right? Everybody knows about them because, like, if you have tried the debugger, you probably have been observing the state of the application. But what we see here are the references, and this is where we can use the renderers. And if I need like a special renderer, I can just create it right from here, right-click, create a renderer, and decide, I want to use the following expression instead of the toString that doesn't exist. For instance, I want to output my name, my first name, my last name, I don't know, company name, company, my company, and the name of the company. So when I have this renderer set, it's picked up by default. Now you can see that it picks it right from here. Actually, in the debugger, the expression evaluator has access to private members as well. They don't have to be public. So in this specific example, I was adding a private method called render that outputs the same string, kind of. So let me set the breakpoint again, where it was right here. And in the renderer, like that could be found in data views for Java and type renderers, I have this client type. So it's created for a specific type. And instead of concatenating the string right here, I can pull the private method from this expression, and let me run the application again, debug. And I can see that it triggered the renderer with the private method invocation. There are more features in the debugger, and I hope you learned something today, and maybe it triggered your interest in the other features as well. So if you want to learn more, of course, all the features are documented, and you will find it in the documentation page. The reason I'm doing this talk is that we are all lazy and not reading the documentation. And if you have any questions for me, catch me. I'm here for the rest of the day, and my DMs on Twitter are open. So if you need to find me, here I am. Thank you very much for coming, and have a nice conference today.